All right, getting into the fun stuff. Probability. So this was practice exam 2, and starting off with how many rearrangements of hello are possible, assuming you can only use each letter as much as it appears. So one letter, and this kind of sets the tone for realizing that there's not 5 possibilities, there's only 4, because we have to watch out for that double L. We don't want to count that twice. So we either have H, E, L, or O. That gives us 4. 2 letters, we want to consider where we could have the situation of a double L. So you may want to even separate that out. You could do that kind of like I did here on 3 and 4. I really could have done that on 2. So a case where you have double letters, there's only one of those, double L's. If you don't have double letters, then you have 4 possibilities for the first letter and 3 for the second, which gives you 4 times 3, 12. So 1 with double letters, 12 without, gives you 13. 3 letter, let me just explain a little bit what's going on here. So I'm taking this is a category, this isn't a fraction, first of all. It's wasn't very clear. So less than or equal to 1L. In other words, we don't have more than one of any letter. And we have 4 letters to choose from. So out of our 4 letters to choose from, we're going to choose 3 of them. And this gives us 3 letters. So it could be E, L, and O, H, E, and O, O, L, and E. It just gives us 3 letters, but it doesn't tell us which order to put it in. That's why we need this 3 factorial. So that's the position of the first letter, then the second, then the third. So that's what happens if we don't have any double letters. Now what if we do have a double letter? So in other words, out of our 3 letters, we have 2 L's. Well, first we choose the other letter. Are we going to have the LL and the H, the LL and the E, or the LL and the O? So there's 3 different choices for the other letter. And once we've chosen that, then there's 3 ways to position. Basically, you can think if you had the HLL, for example, the H could go in the first, the second, or the third position. And the same with the E and the O. So that gives us 9 possibilities with a double letter for a total of 33. Same logic for 4. For 5, we could use the same logic, but we do have a nice formula when we're using all the letters available, which is just 5 factorial would be the total if there were not any duplicates. And then there is a double L, so we divide by 2 factorial. Okay, totaling all that, we get 170. How many different ways can we only have vowels? Well, there's really only 4 of those. We can just list them out real quickly. So 4 out of the total 170. Remember that these 170 are all equally likely, and that's why we can set this probability up. If these were not equally likely, we'd have to work with that a little bit more. Okay, and I tried to kind of set up the answer here with A, B, and C. D is kind of the one that you really couldn't get on your own. Oh, you could, but it would be much more challenging. A, so how many are divisible by 5? Well, I just factor 5 out of both of those numbers to figure out that I'm really going from 20 to 160 and counting every integer in there. So I have my formula, 160 minus 20 plus 1. Same thing with the 3. The little difference here is I have to be aware of 100 is not perfectly divisible by 3, neither is 800. So I want to take a close look. What multiple of 3 will put me in this range? And in this case, 99 would not, so I have to go one more, which is 102, 34 times 3. Over here, similar thing, if I had 267, I'd be out of that range. So I really just want the integers from 34 to 266. Subtract them, add 1, you get your 233. Same thing for C. And then we know the sum rule is if we want A or B, so we want a situation where either this happens or this happens, we take this situation plus this situation, or the number of these events, the number of these events, and then subtract out the intersection. In other words, integers that are divisible by both of them is why I'm subtracting that answer from part C to get my total answer. Okay, Zombie Man here, we're looking at first 3 on his third roll. In other words, there's only one way of that happening. He has to get not 3 on his first roll, which is 5/6, not 3 on his second roll, which is a 5/6 chance, and then he has to get a 3 on his third roll, 1/6. So 5/6 times 5/6 times 1/6. Same way on the second one, it just gets more difficult because that third and fourth roll, he has to continue to not roll a 5. We have the probability that his first 5 will be on the 5th, so he has to have 4 rolls without getting a 5, whereas this person only had to get 2 rolls without getting a 3. So this is much more difficult, and you can either do that through reasoning, or you could show me mathematically that this number right here is higher than this number right here. Okay, this is very blurry, but this is just an interesting use of the binomial theorem. So we're dividing 3 up into 1 and 2, which seems like a crazy thing to do, but then we just use the binomial theorem on this right here. So we have our first element, or our left, if you remember the Q*bert game, the left raised to the power of the n, plus this raised to the power of 0, which is just 1, so we don't even include it. And then we take the total, choose whatever our power is, or how many we're taking of the second element, or really how many we're taking out of that first element. So this could have just as easy been n choose n. And then we keep on going out, and what we end up with is exactly what we wanted to show. So we've shown that 3 to the n equals this expansion right there. Okay, this was a Venn diagram problem. In this case, there were only 2. So we had the lab, and we had the specialist referral. We know that 35% were not referred to a specialist or needed lab work, so they're out here. We also know that this total is going to be 100%. So we know that x, now x here, x is the area in this kind of moon shape. X is not the percentage in that total circle. That total circle would be x plus y. If you label x as that total circle, it's going to get very confusing in the diagram. So when you do a Venn diagram, I recommend that you only label each chunk based on, basically think of it as not being able to cross over any lines. So we know that total is 65. We know that these are 40, and so right away we could find out that this is 25 if we wanted to, or we could set up an equation really quickly, substitute in for our x plus y, and find out here that y equals 5. So several different ways to do that. You could also say, well, x plus y is 40, and we know that's 65 for the total, so this is 25. But then we know that the total of this is 30, and if this is 25, this has to make up the other 5%. Okay, the distinct primes. This is certainly one that I would recommend you writing out a few examples if you haven't done one yet. So maybe just come up with the simplest primes you can think of, 2, 3, 5, 7, and 11. And whatever, if it helps, multiply those out and actually get a value of n. And what we're really curious about here is how many different ways can we split up those primes. Okay, so we could split it up into 0 and 5, 1 and 4, 2 or 3. Notice that 3 and 2 would just be the same as this, 4 and 1, and 5 and 0, so we're not double counting that. And there's only one way to put all 5 in one group. For this one right here, we have 5 elements and we want to choose one of them to be separate, which is just 5 choose 1, even though I didn't write that here. And here we want to choose 2 out of those 5, so we have 5 choose 2. Then we just total the number of ways. Okay, number 7. Here is the situation where we have a few categories. This is like number 2 and 3 on good problem number 2. So 4 different categories. In other words, we have 3 walls. There's always one less wall than categories. And we have 30 coins that we'll be placing in those. So 33 choose 3 total ways. But now we want to look at only 15 quarters, and the other coins we can have as many as we want out of them. So you might try to find out all the ways to get less than 15 or equal to. It turns out that's a little more complicated. It's easier to find the complement. In other words, how many ways could we have greater than or equal to 16 quarters? Well, if we know we have to have at least 16, let's go ahead and cement those in, lock them in. So we have 16 quarters here. And if we have 30 total coins, that leaves us 14 other choices. Now keep in mind that those 14 could be quarters. In other words, we still have 4 categories with 14 coins to distribute now. So add them all up, we have 17 different things. We want to choose 3 places for the walls, or 14, so we could say 17 choose 14 ways. But that's not the answer to the question. The question wanted less than or equal to 15 quarters. Well, all we need to do then is take the total number of ways minus all the possible ways that have at least 16, because if we add up all the ways that have 16 or more and all the ways that have 15 or less, we will get the total number of ways. So this is the number less than or equal to 15 quarters. Same principle with the dimes. So we have 20 dimes, and we don't have a specific question for that, but if we can figure that out, it's really going to make part C a lot easier. So using the same principles, we find out that 12 choose 3 is the number of dimes, so this is just following the same method that we used to get the greater than or equal to 16 quarters. So then we get down here, 17 choose 3. This is the number greater than or equal to 16 quarters. 12 choose 3, greater than or equal to 21 dimes. And in this case, we have minus 0. Now usually we would just subtract out the intersection, and this would give us the union of these two here. But why is the intersection empty? Well, think about it. If this is our first greater than or equal to 16 quarters, and our second event is greater than or equal to 21 dimes, in order for both of those to be true, we would need at least 37 coins that we're going to choose. But in this case, we're only choosing 30 coins. We're choosing a collection of 30. So there'd be no way to meet both of those conditions, so the intersection is empty. So the final step we need to do then is just take the complement of this union. In other words, we take the total number minus the formula here for this, the union of these two events. Okay, and again, if there had been possibilities in the intersection, we would have just put it here, and that would have been part of what gets into this parentheses, then gets subtracted from the total. Okay, and number 8, so I'm going to make another brief video because I only have 20 seconds left here, and I know that this is a struggle for several people yet. So I will make a separate video just for number 8.